Hello. In this video, we'll continue our exploration of logical properties in sentential logic with a discussion of logical truth. Remember that in a previous lecture, we identified a series of properties that apply to different kinds of things. As we learned, validity and invalidity are features of arguments. And in our previous video, we saw that equivalence applies to pairs of sentences. Now we are going to focus on individual sentences and on the corresponding property of logical truth. A sentence is a logical truth if it is true in all circumstances. For SL, we can give a definition of logical truth with reference to truth tables. A sentence is a logical truth, or tautology, we'll see what this means in a second, if and only if it is true at every row. So, if you make a truth table for a sentence, and the column for it only contains T's, then the sentence is a logical truth. But if we find even one row that has an F, then the sentence is not a logical truth. In SL, a logical truth is also called a tautology. However, in formal logic, the term logical truth has a broader use than the term tautology. In the sense we are interested in here, a tautology is a sentence that is true only by virtue of the meanings of the truth functional connectives. For instance, if I tell you that tomorrow it will rain or it won't, then no matter what happens tomorrow, my prediction is going to be true. If it rains, I was right. If it doesn't, I was right too. So this sentence would be a logical truth, since it is true in all cases. Now, to know that this sentence is true, you don't need any special knowledge about meteorology or about any other aspect of the physical world. You simply need to know how operators like or and not work in English. In fact, any sentence that could be represented in SL as having the form X or not X is going to be true in every circumstance. The form alone guarantees its truth. Let's take a closer look at X or not X. Given the assumptions built into SL, there are only two possibilities. Possibility 1, X is true. Possibility 2, X is false. There is no third possibility. This is called the principle of the excluded middle. If the first possibility holds, and X is true, then the evaluation rule of the V guarantees that X or not X is true. Because if one of the disjuncts is true, then the whole disjunction is true. If, on the other hand, X is false, then not X is true. But then, given the disjunction rule, not X makes X or not X true, just as before. So, no matter what happens, X or not X will come out true. And this is all due to the rules that define the meanings of the connectives of SL. There are logical truths that depend on something else besides the truth functional connectives. Consider this sentence. If this stone is heavy, then something is heavy. This is also a logical truth. However, it is not a tautology, since its truth does not depend exclusively on the truth functional connectives, but also on other logical features of English, such as the meaning of the word something and its relation with the phrase this stone. So, to capture the fact that this is a logical truth, we'll need a richer language, like that of predicate logic, which we'll introduce in future lessons. In sum, all tautologies are logical truths, but not all logical truths are tautologies. A tautology is a special kind of logical truth, which obtains exclusively due to the truth functional connectives. However, as long as we are confining our discussion to sentential logic, we can use the terms tautology and logical truth interchangeably. Okay, let's go back to our definition of tautology for truth tables. A sentence is a logical truth, or tautology, if and only if it is true at every row. So let's use a truth table to determine whether sentence 1 is a tautology. Here, I've completed all the columns except the last one, corresponding to sentence 1. We can see that the sentence we are interested in is precisely the negation of the sentence that is immediately to its left. So we simply flip the truth values with respect to that column. The result is a column in which we only have T's. Therefore, sentence 1 is a tautology. Since we have the property of logical truth, we shouldn't be surprised that we also have the property of logical falsity, also called contradiction. As you can imagine, contradictory sentences, logical falsities, are the exact opposite of tautologies. A sentence is contradictory if it is false in every circumstance. And in a truth table, a contradiction reveals itself by being false at every row. All SL sentences that fit the form X and not X are contradictory, since they will be guaranteed to be false merely in virtue of the evaluation rules of the ampersand and the tilde. I'll let you work out why this is indeed the case. We've already seen an example of a contradiction in this video, namely the sentence immediately to the left of sentence 1 in the truth table we showed before. You can see that this sentence is false at every row. This also illustrates the fact that the negation of a tautology is a contradiction. Okay, now let's show that the following sentence is a contradiction. I've completed all the columns except the last one. If you focus on columns 4 and 6 here and apply the valuation rule for the ampersand, since that's the main connective of the target sentence, we can see that we get an F on every row, and this shows that this sentence is a contradiction. Last, there is a group of sentences that are neither tautologies nor contradictions, since they are true in some situations and false in others. These are called contingent sentences. A truth table for a contingent sentence will reveal that it is true in some situations and false in others. So, to be convinced that a sentence is contingent, we just need a pair of rows, one that shows that it has a T and another that has an F. If you find those two rows, you can stop searching. The sentence is contingent. For example, sentence 3 below is contingent since it comes out true in some rows and false in others. Finally, there are some equivalences involving tautologies and contradictions that are worth going over. Learning equivalences like this can be a great help in the process of sharpening your logical intuition. But first, to express them more concisely, we need a couple of special symbols. Let this T designate any tautology. This symbol, by the way, is called the verum. This means true in Latin. And let this upside-down T be any contradictory sentence. This symbol is called the falsum, which sure enough means false. As usual, let X be any SL sentence, whether logically true, logically false, or contingent. So, we'll figure them out together. I'll start by mentioning an SL sentence form, and then I'll present you with 3 further forms, only one of which is equivalent to the first one. Your job is to figure out the correct option. Okay, here we go. The negation of a tautology is equivalent to A, a tautology, B, a contradiction, C, neither of the above. Pause the video if you need to think about it. Okay, ready? The answer is B, a contradiction. Using truth tables, you can visualize it by representing a tautology as a column of T's. Then, when you apply negation to it, you flip the values in the original column from T's to F's, and you end up with a column of F's. But a column that only contains F's can only correspond to a sentence that is false in every row, that is, in every situation, and this is none other than a contradiction. Okay, let's go to the second one. The negation of a contradiction is equivalent to A, a tautology, B, a contradiction, C, neither of the above. And the answer is A, a tautology. The justification for this is completely parallel to the one for the previous equivalence, so I'll leave it in your capable hands. Now to the third one. The disjunction of a tautology and any SL sentence X is A, a tautology, B, a contradiction, C, the sentence X. If you want to pause the video while you think about it, that's fine. Ready? Okay, the answer is A, a tautology. To see why, imagine the ways in which the instances of this form could turn out. And to do that, let's build this abstract truth table for the form verum Vx. We have one column for each of the disjuncts. One is for the verum, which, as you'll remember, is a tautology, and thus only contains T's. We're not specifying how many rows we have because X could be any SL sentence, even a very complex compound sentence. Next, we have a column for our mystery sentence X, but since we don't know what specific sentence it is, the values for the particular rows are unknown. Then we have the column for our target sentence form. So let's try to fill the last column. We'll start with the first row. We know that the left disjunct is true, though we don't know the truth value for the second one. However, the fact that we don't know the value of the right disjunct has no importance. Remember that the valuation rule for the V says that a disjunction is true if at least one of the disjuncts is true. But since our left disjunct is true, this automatically means that the whole sentence is true as well. So our first row must get a T. Now exactly the same situation repeats itself in each row, so every column under our target sentence gets a T, which means that it is a tautology. Thus, our target sentence, the disjunction of a tautology and an arbitrary sentence X, is simply equivalent to a tautology alone. So you can see that the tautology by itself is doing all the truth-making work, so to speak, since the rule for the disjunction allows the other sentence, whatever it may be, to be a free rider. It doesn't make any difference to the final truth value of the sentence. Okay, to the next one. The conjunction of a tautology and an arbitrary sentence X is, and here we have the same options, A tautology, B, a contradiction, C, sentence X. Again, feel free to pause the video if you need time to think. The answer is X in this case. To see why, let's again consider how the truth value of the sentence verum ampersand X depends on the values of its components. So we know that under the column of the left conjunct, the verum, that is a tautology, we have T's exclusively. And again, the values for X are unspecified. Let's consider any arbitrary row for our target sentence. We know that the left conjunct is true, but we don't know the value of the right one. The valuation rule for the ampersand says that a conjunction is true if both conjuncts are true. Otherwise, it's false. So we know that one of the conjuncts is true. So the value of the whole is still undetermined, as it depends on the value of X, the other conjunct. We know that X could be either true or false. Assume it is true. Then both conjuncts are true. So if X is true in a given row, then verum ampersand X will be true in that row. Now suppose that it is false. Then only one of the conjuncts would be true, and the whole conjunction would be false. So we can see that whenever X is true, tautology on X is true, and vice versa. Whenever X is false, tautology on X is false, and vice versa. Therefore, our target sentence, tautology on X, and its right conjunct X will always have exactly the same truth value, and thus, by definition, they are equivalent. Now the next one. Contradiction or X is equivalent to A tautology, B, a contradiction, C, the sentence X. Pause the video if you want. The answer is C, X. I'll let you apply the same reasoning we used before to show why this is the case. Last, contradiction on X is equivalent to, and the answer is B, a contradiction. I hope that you can see why this is the correct option. If you have been paying close attention to these equivalences, you'll see that they illustrate the fact that tautology and contradiction are the mirror image of each other, so that the verum and falsum symbols are duals, just like the ampersand and the V. So here we note another interesting symmetry in the system. You'll be happy to know that we'll still find some of the duals in the future. Well, this is all for now. Goodbye.